Hi, I'm Aubrey Wymark. I am a geologist. I've had an interest in tektites for about 26 years. I've been seriously researching for about half that time, about 13 years. This video was supposed to be for Asteroid Day, which is on June the 30th, 2019. It's the 3rd of July now. I'm a little bit late because I've been working very hard. I've only just found the time to do this video. What I'm going to cover today is I'm going to be using Google Earth to try and understand where the likely area is for the source crater for the Australasian Tektite strewn field. Now, this is a very large strewn field. It covers well in excess of 10% of the Earth's surface. It's also very recent. It's only 788,000 years old. The crater is likely in the order of around 40 kilometers in diameter, possibly enlarged quite significantly, like Chesapeake crater from slumping subsequently. So here we're going to look at some of the evidence that's been published, some which perhaps hasn't been published, and try and draw some conclusions as to where the source crater is and where we need to go from here. Due to time limitation, I'm simply just going to run through everything. I've not really rehearsed it, so I'm going to be working really off the top of my head, so excuse me if there is the odd minor error there. Okay, on to the subject here. So let's get the data up. So firstly we want to know, I've got a lot of stuff on my computer by the way. Google Earth keeps crashing. It doesn't like the amount of data I've got on this system. So okay, let's first look at all the Australasian tektite localities. I've got this, this has crept in. Right, let's have that one back. That's the layered tektites. So the white dots are areas where microtektites have not been found. The black dots are where tektites, Australasian tektites specifically, have been found. Let's make the land area white, and it's a little bit easier to see then the distribution of Australasian tektites. These two, by the way, they're probably not genuine. I seriously doubt them. So we've got quite a few off into the Indian Ocean here. We've got some even in Antarctica here. All this has data. I did this some time ago, many years ago, 5-6 years ago. I update it occasionally. We've got tektites going out into the Pacific Ocean here. A lot of data in Australia, some in the Philippines. You get the odd ones there. So this is the distribution. I should move myself there. So you can see this huge area of the Earth covered by tektites here. We can have a quick look at some of the other strewn fields if you like. I needn't turn that off. Let's look at ivory. Oh. 1 second, bear with me. Too much data on this system. I obviously just clicked something that has everything there. Right, let's have a look at the Ivory Coast strewn field. So here's the Bosumptwi crater. These are the Ivory Coast tektites here, in the Ivory Coast obviously. This is in Ghana. And here we have microtektite distribution here, these pink dots. Central American. Okay, here's the probable crater here, and they're over here. Right, North American. This is Chesapeake crater here, and this is the distribution of North American tektites, mainly over here. These are the Georgiites, and these are the Badiasites here. And there's some microtektites down here. Libyan desert glass. I didn't even realise I had that on there. it's possible craters here. I've not looked at that for some time. Darwin glass, okay, down to Tasmania. I've lost it in the Sea of White. Where is, I have to find Australia. Okay, Darwin glass is a really small distribution here. They're not really true tektites. Some of them are just getting onto splash form, but they're not really. So here's Darwin crater, very small crater. I think it's 1.2 kilometers in diameter, if I remember rightly. Very small. You compare that with the Australasian strewn field. Okay, I think I've got too much data in there. Yes, let's get rid of that one. Get rid of that one. Okay. Bear with me again. This is why my computer hates me, because I've got too much data there. So there's the Australasian Tektite strewn field, and Darwin 1.2 kilometer crater, tiny little thing down there. So let's scroll down. What ones did we not look at? Let's skip that. Let's look at Central European. These are the Moldavites. They're from the Rice Impact Crater. You can see it's a bit bigger. That there you go. There's the distribution. It almost looks like two ejector rays there, and the Steinheim crater there. So Eocene pyroxene spherules, we'll skip them. Okay, on to the, let's turn all them off. In this talk we're interested in the Australasian Tektite strewn field. Bear with me, it's going to get more interesting. There's a lot of data to run through. Okay, so we're back here. So what is the distribution? Let's have a look. Now, one of the techniques we can use, just purely using the distribution, is regression. Before we get onto that, let's have a quick discussion. These ones in this area here, in Indochina, these are all proximal tektites. They're splash form type tektites. They're dominated by plastic deformation. They basically formed within the atmosphere. Here we have the Philippinites, we have Malaysianites, and here's Belitung. These are all very similar. These are medial type tektites. These are they were plastically deformed, but they're more dominated by spallation, and they did not ablate. And then you've got the distant Indian Ocean ones and your Australites and your Java tektites here. And there's even been one found in New Zealand. It may have been transported from Australia, but I think it could possibly be genuine there. And these are ablated forms, so these are your most distal tektites. The most distal tektites were the first formed tektites. So very quickly here we're establishing these ones are the furthest away, these ones are medium distance, and these ones are very close to the crater. So that's our first clue, and that's a very obvious clue. I'm not going to go into too much detail there, but if you look at the morphology of a tektite, you can pretty much tell precisely where it's from. I mean, you can even tell the difference between a tektite here and here. You can tell the difference between a tektite from here and here, no problem. You can, if you look at a tektite and you've studied them a while, you pretty much know where they're coming from. And you can tell the distance. Now, one of the things, how do we quantify the distance here? Well, earlier I showed you the Chesapeake impact crater. Now, this is a useful one to compare with, because we actually know that we know the source crater. It's been geochemically linked. Let's move me out of the way. Let's move me back in the way, because I've ticked the wrong one. I've ticked Central American, not North American. Okay, so we've got North American. Okay, so this is the Chesapeake crater. It's about 35 million years old. It's roughly a 40 kilometer crater, expanded to about 85 kilometers. So these are proximal tektites here. So they're about 800 kilometres away. One sec. Right. These are proximal as well, 300, 600 kilometres away. These are all proximal tektites. These badiacites, these are medial tektites. They're very comparable in morphology to philippinites. So these are 1,950, 2,174 kilometres, roughly 2,000 kilometres from the source crater. Now they're comparable to philippinites, so philippinites are probably in that similar range. So we go back to Asia. Right. I live in Manila, by the way. That's where my interest in tektites, it's not where it started. It started in the UK. My first tektite was from somewhere here. But it soon became an obsession when I moved to the Philippines. There's a lot of tektites there. So, okay, let's take philippinites. They're probably, let's say it's about 2,000 kilometres away. It could be a bit less than that. So you're looking at this kind of distance. These ones, again, these are they're very similar to badiacites. These are bilitinites, about 2,000 kilometres away. So we're getting the general impression. Now we know these are the proximal tektites. We can also look at moldavites and the distance they are. So we expect these proximal tektites to be occurring sort of 300 to 900 kilometres from the impact site. So you can see the distribution. It's likely somewhere in the middle of this distribution or at one end of this distribution, but certainly within about 900 kilometres of all of these proximal tektites. Okay, so I'm not going to go into morphology. That can be for another video, another day. But you can, there are very clear morphological signs, and you can look at the morphology of a tektite and tell approximately the distance from the source crater. So let's look at tektite regression. Now we're not looking at any morphology or anything. We're looking at simply the regressing a tektite locality back to a potential source crater, which can be anywhere. There's lots of potential source craters suggested. Okay, here's Storfa, 1978, suggested here. Now, what I'm looking for here in the regression is, firstly, when you look at the moon has ejector rays. Everything has ejector rays when you eject material. And remember, in such a large impact, the bulk of the material is really forming above the atmosphere. Or the bulk of the atmosphere, so you're going to get ejector rays. So what we're looking for is a point here. So this is Storfa 1978. This is Hartung and Rivolo 1978, 1979. What we're doing is we're going to be looking for the maximum amount of overlap. You want to be seeing distinct rays forming. We can zoom in and get more data. I want to see distinct lines here. I want to see distinct lines here. Distinct lines here. The more overlap that you're getting, it's indicating you're closer to the source, because you're actually then projecting a ray and not randomness. On top of that, what I want to do is I want to be seeing a bilateral symmetry on the distal ejector, because it was a very oblique impact. And the proximal ejector, this area here, I expect to see more of a radial symmetry. These were the last formed tektites, so they're forming as the crater, the spherical crater, and it will be nearly spherical, probably be slightly elliptical, but as a basically spherical crater opens up, so I expect a basically spherical distribution for the proximal tektites and a bilateral symmetry for the distal tektites, albeit one which is partial because we have large areas of ocean where we have no data. So we're looking for overlap. So what we do is we plot all these potential craters that have been published and then see how they work. This one, for instance, works very badly because all your proximal tektites are up here. These are medial tektites and they're closer than the proximal tektites. It's not working, and there's not a whole lot of symmetry there, not a whole lot of overlap. So we keep going with these. There's many published localities. You don't have to use published localities. I have an Excel spreadsheet which you can put in any location and then regress thousands of tektite localities back. So we keep doing this and then analysing each of these localities. I won't do every one because I'm just going to bore you, but some work better than others. And then we get to, okay, let's unclick that last one. Ma et al. Okay, this is working pretty good. Right, if you look at this, let's move me back up here. If you look at this, I'm getting quite thick, dark rays here. I want to see, as I zoom in, I want to see as much overlap as possible. The more overlap, and that's looking pretty good, pretty solid black lines, that's good. You see it's in the middle of this area of proximal tektites. So we expect a radial distribution here. I expect a bilateral symmetry here, which I'm getting. I'm going to look at this butterfly ray and this butterfly ray. What is the distance between this? Where's the central point? There should be something, these are downrange rays here. So I'm expecting this. This is making a very nice pattern. This is what I'm expecting. So this locality is good. It's a distinct possibility here. Let's look at some of the other good ones. Trinker et al. 2009. Again, I'm not sure quite as good overlap, but it's pretty good overlap here. You're getting distinctive rays forming. You're getting a good bilateral symmetry here. This is the downrange area. Now, what is the downrange ray? Is it this ray? Is it this ray? Is it in the middle of these two? Or is it somewhere here? The downrange is around about here. I always work on about 164 degrees. The impactor came in from here, impacted shallow angle and ejected. Now, again, a nice, it's basically in the center of this area. This is looking very good as a potential source crater area. This is me, Wymark 2013. Did I introduce myself? I'm Aubrey Wymark. So this is my contribution as to where I think it is, and I will later run through why I think it's here. Now, if we're to analyse this, okay, these rays, very good, very nice dark overlap, similar to the other ones. In terms of placement in the middle of this area of proximal tektites, not quite as good. Really, you want to move it a little bit over to the west here, you get a better distribution. But let's not forget that here, South China Sea, this is all ocean. So are the tektites here? What is the distribution? Are the tektites here? I mean, I don't know. So possibly that could be the centre of distribution if you envisage that there are tektites that are going around here. So we don't know these areas because they're covered by sea and buried by sediment as well, no doubt. So, okay, pretty good bilateral symmetry again, pretty nice. This is forming a nice ray here. It appears to be something coming through here. Somebody wants to have a look over here for tektites. I think there was one found somewhere here. I'll have to dig that reference out. I didn't get a precise locality, I think, so that's why I didn't plot it. So looking pretty good here. So really what we've done by doing this exercise, let's look at this Kenkman 2014. See, this doesn't work. Here is the proximal tektites here. These are medial tektites, so they should be the same as proximal tektites. They're not. This doesn't work. There's no symmetry. There's not a good overlap of the lines. It's not working. So really what we come down to here is the tektite source location is likely in this area here. In fact, around about here is probably the best spot. I'm picking it around about here. Other people think it's on land over here. I'll explain why it isn't later. But it's in basically this area. It can't be anywhere else based on regression, not logically. Right, so okay, I've quickly covered tektite and microtektite, well, not really microtektite regression, this is just tektite regression. I will cover microtektite regression in a little bit. Let's do microtektite regression now. That would seem like a good idea since we're talking about regression. Right, Glass and Coble, 2006. Okay, alright, I was working on a grid here. I think I've got these elsewhere, possibly as an overlay. Let's have a look. Well, I should have them. As I say, I'm a little bit unorganized here due to time limitations, because I have had to work. One of these things, you need to work for money. Right, okay, I can't see them, we'll cope with these. So imagine the distribution goes back there. But basically they've regressed. This is Glass and Coble 2006. Now let's have a look at where the microtektites are. Bear with me. Let's turn off all of these tektite localities apart from microtektites here. Okay, so these black dots are the microtektites. We've got a limited data set here, and we don't have any nearby, and obviously we don't have any microtektites on continental areas. Microtektites, as soon as they come into contact with very slightly acidic water, they're just basically dissolved. They disappear. They don't survive. The only place where you get microtektites on land is Australia. In some of the salt lakes, very salty waters and alkaline conditions act to preserve tektites. So that's an aside. They've regressed it back to here, this area here. I think it's regressed too far back, but it's on the right line here, basically. Let's have a look at another one here. Zooming down, I've got lots of junk here. I'm visiting Sudbury in a couple of weeks, so I've been planning my trip. Looking forward to that one. I'm going to teach myself. Right, so here is Prasad 2007. So again, it's regressed back to a similar area, but again you have this problem of lack of tektites to the north constraining it, and lack of anything really close by. A lot of it is quite far away, but it's gone to this area here. Next one, Glass and Pizutu, if I pronounce that right, 1994. Now they've got a slightly different area here, but you can see it's being regressed back to the Indo-Chinese area. So that's basically as good as we're getting there. So this is what I was saying earlier, with using the regression techniques of all the tektites, coming up with this area being the most likely. Right, so where shall we go from here? That's the main thing. So we've basically defined that the tektites are coming from here. Let's look at layered tektites now. Now, are these really tektites? They're more of an impact glass. They're the lowest temperature tektites, the least melted bodies. Let's go up here, find through all this mess. Right, let's turn microtektites off and turn layered tektites on. Right, so here's the layered tektite distribution. This is an old file because it's not updated. Okay, anyway, we'll live with this. This has got most of the localities on. There are some new localities, interestingly. I will be publishing this. I'm planning on doing that next year. I have some Mungnong tektites. There's some old ones from Zambales, Manila area, and also now from the Bicol area. They're kind of transitional somewhat. They're not really quite the same as the Indo-Chinese ones, but they're following this butterfly ejector ray out. The bulk of the layered tektites are here, and there is an area here in Laos and the southern part of northeast Thailand, this area anyway here, which it's dominated by layered tektites. It's dominated by the lowest temperature tektites. Let's plot that. So okay, this doesn't like my thing. So this area here, this red area here, this is mainly layered tektites. You're not really getting many splash form tektites. Excuse me 1 minute, let's grab a drink. Okay, so right, this is the area where the lowest temperature tektites occur. So the logical thing for a lot of people is to simply put the crater in the middle of this distribution, and that does seem quite logical. But there is also another explanation here. Let's get the main butterfly rays up. This be the Manila Bickel ray. Okay, well, I'm plotting to where I think the crater is. It's Indian Ocean ray. Okay. Right, so these are the two butterfly rays which go off to the side, and then you have downrange rays here. Now the other explanation here is that this area of low temperature melt is along a butterfly ray, which is a very prominent ejector ray, and the other butterfly ray is probably here, and you simply do not see this. It's in the sea, so you're seeing half a pattern here. That's most likely, and to support that, you know, we get the odd transitional type of Mangnong flung all the way over here, and that is some considerable distance. Let's measure that distance, assuming the crater's here. It's in this rough area. So we've got them ejected 1,630 kilometres. I'm really getting in the way here. So along these rays, potentially you get some transitional types here. So I think that there is quite a likelihood that the other butterfly ray also contains a high concentration of layered tektites here, which you're not seeing. You get some in Hainan and the Laizhou Peninsula, but the bulk of the Mangnong tektites are in this area here, and you find them all around here. But here occurring with splash form tektites. So distribution there, it really has, a lot of people think it's on land. I'll explain why the crater cannot be on land later, but I think that this is probably one arm of a butterfly ray where you're finding these things. Let's turn them off. Okay, there's other distribution maps here. Let's have a look. Whilst we're looking at Mangnong type tektites, so let's say yes. Okay, so that is actually from Schnetzler and Bacone, 1996. So you can see there. I think I took it from this publication. It might be. Some of the plotting is slightly off. The grids are off. The outlines are slightly off. You get approximately the right place, you get the message there. So possible crater in here or somewhere around here. I'll explain that later. You also get so layered tektite distribution, perhaps another arm going there. What else have we got? Right, we've got let's have a look at the geochemistry of the some of the layered tektites. Now, this is CaO, calcium oxide distribution. So again, it seems to be leading us wanting to go into the Gulf of Tonkin or somewhere here. So you end up with this kind of area for the crater. Schnetzler 1992, that Schnetzler 1992. Sodium oxide. Again, this is the distribution. It's increasing here, so it's probably the crater somewhere in this area here. Silicon dioxide concentrations. So the lowest concentrations are here. So it's almost swinging around here. So maybe somewhere in this area here. So, okay. Right, what shall we do next? Let's have a look at some of the overlay maps. Right, I did an overlay map project. One way to try and determine where something is you take all the possible points, you overlay all the data, and you come up with basically a heat map. It's pretty crude, some of the data's not valid. So, Mesozoic sediment here. Some people have said from the rubidium strontium data that the source rock is probably Jurassic, about 170 million years old. This is Blum et al. So look for where the Mesozoic rock is or the Jurassic rock distribution is. Possibly a crater on that. I'll explain that later. Beryllium-10 iso concentrations, Ma et al. They put the crater here. Basically, the lowest beryllium-10 content will indicate where the crater is, because beryllium-10 is a short-lived cosmogenic isotope. It has a half-life of, test me, 1.39 million years or thereabouts. So it decays fairly quickly. So the fact that it's in these tektites, the most deeply excavated tektites, is telling you something actually. It's telling you that the source rock is not Jurassic in age, it's actually a young source rock, and it's obviously a very rapidly deposited sediment for these last produced, deepest excavated tektites to still be containing beryllium-10. It's obviously a fixed sequence of relatively young rock. This is where the source crater must lie, and it's lying in this kind of area here. Blum actually picks the potential source crater somewhere here, which makes very good sense. It's one of the best areas to propose it, actually, somewhere here, close to the coast of Vietnam. It won't be totally close, I'll explain that in a little bit. Crater absence. Well, let's explain it now. Okay. The crater cannot be on land. This is a very recent crater. It's 788 million. 788. If it was 788 million years old, you can have it on land. It's not. It's 788,000 years old. In that time, you cannot erode much sediment. In fact, you could probably erode a few hundred meters. You can't lose a crater in that short amount of time. The cratering effects probably go down quite a lot, perhaps up to 10 kilometers, but certainly a decent 3 or 4 kilometers without a doubt for pretty serious effects. You can't erode that much sediment. Indochina has been explored geologically. It wouldn't be missed. And what wouldn't be missed the most is the fact that in this tropical to subtropical area, craters form lakes, even small craters like Lunar crater, Bosumptwi crater. It forms a crater lake. Let's find Bosumptwi crater. Let's have a quick look at it on Google Earth. It forms a lake, and this crater is about 1 million years old, or a little bit older than 1 million, 1.1 million. Again, I'm working off the top of my head. Okay, this is an impact crater, a recent impact crater, not too dissimilar age from the Australasian impact, a little bit older, and you see you've got a crater there. This is 10.5 kilometre crater. So, where's the lake in Indochina? That's pretty obvious. We want a 40-kilometre diameter lake in Indochina. There isn't anything here. Really, the only option is Tonle Sab, this long elongate feature here. It's simply in the wrong area for the tektite distribution. It's simply too far west. All the proximal tektites are over here. It cannot be the source crater. This was proposed by Hartung et al. In 1994. It's not the source crater. It's impossible. So there is no circular crater lake on land here. It's simply not on land, and there's other reasons why it's not going to be on land. Primarily the beryllium-10 content. You need a fixed sequence of young rock, an abnormally fixed sequence of young rock, to produce those beryllium-10 iso concentrations. Now, some people argue that the rubidium strontium says a Jurassic age, beryllium-10 says a much younger age. Well, obviously you have to go with a much younger age. It's the only one that works. Some people say, obviously you've got soils and they've mixed with the Jurassic rock. That's how you've got both of these occurring together. It doesn't work. Tektites are incredibly poorly mixed. I mean, they're shock melted rock. They're not well mixed rock. This argument does not work. You can find ways around it. Now, if you have very rapidly deposited sediment, then the rubidium strontium clock is not necessarily reset, particularly in, say, a deltaic environment. Sea level goes up and down. This Gulf of Tonkin is about maximum 50, 100 metres, about 100 metres water depth. Goes up and down in glaciations, interglacials. It's fed by rivers along here. The Red River is the main source of sediment. There are some sources of sediment here. Red River is by far the main source of sediment, coming basically from the Himalaya area. A lot of sediment coming into here. This is a pull-apart basin, extremely thick sediments here. We go over that in a little bit. Okay, so all this evidence is really pointing, and if I've forgotten anything, I'll come back to it. Let's have a quick look if I want to cover anything else. Okay, no, let's skip all that stuff for now. Okay, I'm sure I missed some stuff, but okay. So what we end up with is saying, right, there's no crater on land, there's no big circular lake on land. We need a very fixed sequence of recent sediment. We need silica-rich sediment, obviously, to produce tektites. Tektites are only produced from silica-rich sediments. Continental shelf areas are perfect for producing tektites, hence the Chesapeake impact crater position. Continental shelf area, most likely. Abnormally fixed sequence of very young rock. Okay, everything points here to the Songhong Basin or Yinghai Basin. Yinghai Basin is Chinese, Yinghai is somewhere here. Songhong Basin is the Vietnamese name for this basin here. So that's why I sometimes call it Shai Basin. Songhong Yinghai Basin. Then I don't upset anybody. So the delineation, I'll show you the maritime border here. Okay, this is the maritime border. This is Chinese side, this is Vietnamese side. It stops here. They've not decided on where it goes after that. Okay, this is the agreed maritime boundary. Okay, so that gets me thinking, okay, probably in the Songhong Yinghai Basin, you have extremely high sedimentation rates. You have about 17 in the depot center, which is about here. You have about 17 kilometers of tertiary rock. I think mainly Eocene to recent, so about 17 kilometers in the last 45 million years or so. And A lot of that is even more recently in the Pliocene, Pleistocene sedimentation rates have increased. So very, very fixed sequence of young rock here, abnormally so actually. You've got sedimentation rates, very, very high sedimentation rates. I'm trying to think of a number, but I think it's about up to 70 centimetres per year. No, sorry, 70 centimetres per 1,000 years, something in the order of that. It's very high sedimentation rate here. Anyway, I can't remember the exact numbers right now. So you've got extremely fixed sequence of rock here, perfectly in line with what we're seeing with the beryllium-10. That is a massive clue. So, okay, there's no crater on land, no crater lake on land, nothing obvious on land. So if you can't erode a crater, because you cannot erode a crater in 788,000 years, you simply cannot do that. But you can easily bury a crater, especially if you have high sedimentation rates. So this is another clue: we perhaps have high sedimentation rates. If we can't see a crater, maybe it's buried. And you do require quite high sedimentation rates to bury a crater in that short time, but it's possible. So that got me looking in this area here. Clearly, this is a sign. So start going through the published papers. There's hydrocarbon exploration, mainly for gas in this region. In fact, there are some productive gas fields. There's also carbon dioxide there as well. It's not all productive. And okay, so in this area, a number of wells have been drilled. There has been seismic exploration as well. I'll come on to that. So it got me starting looking through the papers that are published on this area. One thing that struck me very early on, let's go with this. Let's not go with that. I'll come to that in a minute. Okay, if you look, I'm looking for obviously a circular feature. I'm looking for a crater. So some of these things, diaperic structure. Now these are shale diapirs. They're believed to be caused by overpressure. So then the shale basically rises. It's a bit like a salt diapir. It's the same principle. The lower density material rises. Now I start seeing this circular pattern. Now, by the way, with all these papers, many are not well defined exactly where they are. Some of them have a grid, but then the country outlines don't work with them. Others, the country outlines work. And so which is it, country outlines or grid? Some of these are very commonly up to 10, 12, 15, 20 kilometres off in terms of uncertainty where the features are. Some of them are up to 40 kilometres uncertainty. Now, whether or not this is carelessness or whether or not this is deliberate in order to publish oil industry data and it's blurred the lines a little bit, I don't know. There's a lot of inaccuracies in some of these papers as to precisely where these same features are. I'm hoping to be able to work on getting better resolution to really tie them in. They're coming in a similar place, but they're not precisely placed, not amazingly for scientific papers, significantly off between the publications. So you're seeing this circular feature here. This stood out to me as something potentially very interesting in these publications. So first one was Z et al. 1999, then Liu et al. 2002. This is Yin et al. 2004. Again, this feature is standing out here. This is Li et al. 2011. And suddenly, I'm getting a lot of interest here. You seem to have a circular feature here. There also seems to be potentially a circular feature here, possibly parts of one there, but certainly seem to have a circular feature here and a possible circular or elliptical feature here. It only goes on the Chinese side. What's happening here in Vietnam, I'm not sure. There may be a mirror image. So there's potential here. It's looking interesting. You're getting a circular feature. Now the traditional view is that these are north-south features and it's a pull-apart basin. So you get on echelon type stretching, and this is why the diapirs have come here. So you're looking north-south, but I don't just see a north-south, I see a kind of circular pattern potentially. Again, the positioning is not necessarily precise. Here's another one. This is Lee et al. 2015. Again, I'm looking at this possible. This kind of looks circular. This kind of looks elliptical to me. Interesting. No, these are all the seismic lines. We'll come back to them. Okay, so, alright, those shell diapirs, I'm not saying they're formed by impact. Maybe they're following lines of weakness associated with impact, possibly. Any circular feature is going to draw my attention, particularly a circular feature in roughly the right area. So that got me looking at other data. So we have Gong and Lee. I think this is 1997. Right, it's in Chinese. I don't speak Chinese. My landlady used to speak Chinese, and she translated some of this for me. Let's work on this last one there. She said area not properly documented. It basically means chaotic sediment in some of the subsequently published papers, which basically copy this. This is the S30 to S27 area. This is Pliocene basically. So this area is chaotic. They can't plot the sediment isopachs as they have done through the rest of the field because this area is chaotic on the seismic. This is the Miocene Pliocene level, a little bit smaller chaotic area. And this is the Miocene area. There seems to be a circular feature in this area here. It's becoming plottable. Here's Yan et al. 2011. He's basically copied Gong and Lee. So you've got this question mark here. This is sediment isopach map for the Pliocene. You can see incredibly thick, up to 2,000. I presume this is meters. Of sediment in the Pliocene, 2 kilometers of sediment. And this area, they don't know how thick it is. It's all chaotic. It's messed up. Question mark. Chaotic sediment obviously interests me. This is the late Miocene area. Chaotic sediment there. So that's interesting. I haven't got the seismic, but there's clearly a chaotic sediment in the Miocene Pliocene area, so that's very interesting. And corresponding strangely with this diaperic structure that seems to ring it. So this is immediately drawing my attention to this area. I'm thinking the crater is definitely in the ocean here. It's in the Yinghai Basin. It's got to be where there is a high sediment thickness. There's a really good map of showing sediment thickness, but unfortunately I haven't. I don't think I uploaded it. What do we have here? No, nothing here. I didn't upload it there. But what we can do, there's thick Pliocene sediment. Well, this is where the thick Pliocene sediment is, basically in the centre of the basin anyway. So your crater is likely in this. I think we ran out of data here in the Vietnamese side, but basically in this area here, this is where it's not going to be right at shore, but a little bit away from the shore. So your crater is likely in this area here. So this is where we need to be looking, and you've got this area here where you've got circular feature. You've got chaotic seismic as well. Alarm bells ringing. Okay, next thing. Have a look at the gravity data. Now, there is freely available gravity data on GeoMap app. Anyone can go to this website and look at the geophysical data. It's quite limited. Data is quite low quality, but it's free. and it's better than nothing. So what do we see here? I mean, there's a number of features you might be picking out, but my eye is drawn to this feature here, which looks distinctly circular here with an area in the middle. So this looks like a circular pattern, and again it's broadly corresponding with where we're getting our shell diapirs, which seem to be in a circular pattern. Now that's again, there is a margin. By the way, the gravity data is accurately plotted. This is accurate. All the other data taken from scientific papers with the shell diapirs and that, honestly, you can move them up to 20 kilometers, no problem. Uncertainty as to how I'm plotting them when I superimpose them on this. They are the country outlines versus the grid are not accurate. It's not working well, so I'm not sure where they were taking their maps from, or if they were deliberately skewed or accidentally, but it's hard to be confident in how they're overlaid. But you've got a very similar area, put it that way. So circular pattern here. Let's look at the circular pattern there. It's causing me interest there. So on this is the GeoMap app, Booga gravity anomaly. You've got the free air. It's this feature here which to me stands out as being circular. There are other features here, this elliptical feature which could be of interest, or this feature here, and they're perhaps almost better placed, but this is the feature which really stands out to me, and it's corresponding with the other data. As a geologist, I'm always looking for overlap of data, multiple lines of evidence which are drawing you to one point and drawing you to the same conclusion. I never base a conclusion off of a single line of evidence or a single piece of evidence. That simply does not work. You have to see multiple lines of evidence, and the more lines of evidence you've got which are not saying that you're wrong or not contradicting one another and are agreeing, the more likely you're going to be coming towards the correct answer. Not necessarily, but more likely, greater likelihood. So we're looking at this feature here. Okay, these are the same maps plotted differently. Isostatic map. I mean, really, when I look at this, it's fairly low resolution. This feature, to me, it just stands out. I mean, when I saw that, I thought, wow. That is exactly within a very small area. I think it's within 20 kilometres where I thought it should be, but I think that's just because of the inaccuracy in the mapping. But that feature stood out. Okay, so I went to a company in the UK called GTech, and they were very, very helpful. They provided me some higher resolution gravity anomaly data. It's basically the same gravity data as it's the 2012 data. The same data is on GeoMap app, but as you can see, it's better and it's been manipulated. It's nicer. So this is the free air 100 kilometer pass. This is the free air pass here. Let's have a look at this. It's a bit better. Again, you see this blue area, semicircular kind of pattern, and you kind of see what looks like a ring here. Interestingly, again, multiple lines of evidence. Okay, if I take the measurements of that ring, what I think is a ring. I have to move me now. 45 kilometres. Well, when I measure it accurately, I came up with about 43 kilometres. What we're ending up with is a feature which looks circular. 43 kilometres. Anyway, roughly around that. We're ending up with a roughly circular feature, or very circular feature, which is around about the 40 kilometre mark, which is the best estimate of the size of the source crater. We think it's going to be a similar size to Chesapeake crater, so I would be looking at 40 kilometres plus minus, with some slumping which might have enlarged it to maybe 80-90 kilometres in diameter, but your main crater is going to be about 40 kilometres in diameter. So this is 43 kilometres. That's pretty close. So again, matching. What was disappointing is I got some higher resolution data from GTEC in 2017. Now this data was using more satellite passes, so therefore it's higher resolution. It should have provided a better picture. This is it here. Unfortunately it's not, and you're kind of losing a lot of the features. At first when I saw it, I was very disappointed. I was hoping it would really show up something nice. But it's not the end of the story. Maybe it is showing something here. I mean, I start to see a circular feature here. Maybe I just have a vivid imagination, but I kind of seeing a start of a circular pattern here. I'm wondering if we're picking up something that's a bit larger here, that's capturing basically a slumping area into a central circular crater here. So you've perhaps got this larger area here, which is more elliptical, because this was a very oblique crater. Now, although a very oblique impact, now even though it's very oblique impact, we are expecting basically a circular crater, but it's not going to be absolutely perfectly circular. And in terms of the way that it will be effectively dug out during the impact is, let's find some data. It's far better that I show you a picture. Now again, I'm working on the fly because I've not actually prepared anything properly, and when it comes to the Gulf of Tonkin papers, I am not particularly well organised, but I know I have some images somewhere from a paper which will be quite revealing. And you know, if I was organised, I would have planned this properly in advance so that I can show you, but I'm not. And the data could be in many places. Right. Okay, so I've got all sorts here. Got bits of Chesapeake, got other impact craters. Perhaps I need to find the original paper. Which I can't even remember properly. Right, this is something we might need. I'll tell you what, this one here, maybe this is possibly not the actual paper I'm thinking about, but potentially it's going to have what? Oh yes, okay. Well, this is what I'm after. So with an oblique impact here, let's say we've got a 15-degree impact. I always use about 17-degree impact for the Australasian strewn field. Let's make that bigger. Let's move me out the way. So let's use 15 degrees. So if it's coming in this direction, or it could even be under 15, who knows. But what you've got is you've got this area here is more deeply excavated, and then downrange it's smoother. So you've got an asymmetrical shape in an oblique impact. It's still going to produce a basically circular, almost circular crater, but it's asymmetrical. So what I would expect from that is the subsequent slumping may result in more of an elliptical pattern. So the crater itself would basically be circular, or nearly circular. This is a 7-degree impact crater. It's basically circular. The crater will be basically circular, but it's not in cross section. It's not the same. You know, you've got this sharp rim on the uprange area, and then smoother on the downrange area. So I think this is important, because with subsequent modification, you may well find that you end up with an elliptical modification to the crater. So although the central crater is going to be circular, the wider area, which is then slumped in, is perhaps going to be more elliptical, and this might explain some of the more elliptical patterns that we're seeing. Maybe we are seeing a little bit more of the crater here. So this is 100 kilometre pass, this is the 10 kilometre pass. These are all from GTEC, very good company in UK for your geophysical needs. So I'm a bit disappointed, I've kind of lost the crater there, but maybe there is a larger feature here which represents slumped material. So you might be looking at 56 kilometres perhaps by 43 kilometres or so. Let's overlay this GTEC data, let's keep that there. This is the original one, remember. I don't know why Google Earth does that. Let's get rid of this one. Okay, so let's turn this on. Okay, so this is the 2012 data, 2017, 2012, 2017. I don't know. They kind of overlap, but is there anything there? It's difficult. Certainly on this data, I was disappointed when I saw this data because it's not really showing me what I really wanted to see, but maybe it's showing something. Nonetheless, we don't necessarily throw all that old data in the bin because there's a lot of stuff there, but it's something to think about. I mean, I still potentially see some circular features in here. As I say, maybe I have a vivid imagination, but I still, when I see maps like GeoMap app and I'm seeing this feature, to me it gives me a lot of hope that maybe there is something there. These are other gravity anomaly maps, some older ones, low resolution. I don't know, you need a good imagination there. This one I'm maybe seeing a bit more feature here. Maybe there is something here. And I kind of see a circular pattern just going around there. I don't know if you can see that. Let's take a measurement. 53 kilometres, against a similar number. We had 56 kilometres on that last bit. 52 kilometres. I don't know. I mean, is there something there as well? I mean, again, eye of faith. I'm not sure there's enough. Gravity anomaly data is never going to give you the solution. It's going to give you a hint that there's something perhaps worth looking at here, and I think it's giving that hint. It's not solid. So we've got a number of pieces of evidence which are lining up and layering on top. So that makes me think that this area is potentially good. When I did the map project, by the way, let's get rid of these. I did an overlay project, taking all the data, making a heat map. This is where the crater most likely is. You throw all the data in. There's not any data, but every possible bit. Some of the data is going to be misleading. It's not right, like the Jurassic sediment, but throw that in anyway. All the potential data, and the redder the area, the more likely the source crater is. So what we end up seeing is this area here is probably where the source crater is. Like I said, I do not believe it is on land. It would be obvious. There's going to be an obvious lake, and if there wasn't a lake, there's enough geologists that would have found it. You know, it's not going to disappear in that short amount of time, a 40 kilometre diameter crater. So it's buried in the sea. So, okay, here's our heat map. It looks like this area, most likely this area here, which is exactly where Mark et al. Said. So this gravity data is, to me, saying this area here, where my hand is here. This data is saying perhaps somewhere over here. Now it can't be too close to shore because the sediment thickness isn't great enough. So really it's got to be kind of in this area here. Certainly going to be in this area here. That's where all the evidence is pointing. So what other data do we have? Here's our chaotic seismic here. That's very interesting. Okay, so we've narrowed it down. I'm not sure I've quite covered everything, but that's the bulk. What we want is seismic data. I'm going to put that map up there, the gravity up there, because then I can see where what I'm wanting to see. Now, I recently discovered this line is for sale. It potentially covers this gravity anomaly, not in an ideal place, but it's nearby. So I'm going to try and get this seismic line. It might be too expensive. I've got no idea. I work in the oil industry, but I've got no idea how much seismic lines cost. But one can but ask and see if it's reasonable amount, or if we can blag it. I'd like to see that line. I don't think it's going to be definitive. I certainly wouldn't spend a large amount of money. If it was here, I think I'd pay anything, sell my house to get it. But this one is, I don't think it's going to tell you a huge amount. It's going to hint. Now let's look at, we had some gravity data, Lee et al. Now Lee et al., not all these gravity lines are actually available. He's published a low resolution line here, this darker line here, line 0755. Now this potentially covers the edge of this gravity anomaly, which is in this area, potentially just cutting the edge. So not ideal, but very interesting. This line here, which is not available, this is very, very, very interesting. I would like to get hold of this line. Now, I'm not sure about the exact positioning. Okay, we got grids, but this is aligned to the grid, by the way. But look, the land area doesn't work, so maybe it's shifted a little bit this way or a little bit down here. It's not quite working there. Anyway, I would like to get this line, and I would like to know exactly where that line is. This line is the only one we've got to work with, and it's very low resolution. So let's have a quick look at that line. Where is it? Oh, by the way, I'll show you. This is my Tektite library. I've got everything here. Scan it all in for personal use, because I travel most of the time, so I'm never at home to read the hard copy. I prefer to work off paper, but I can't say. There's about, I think, 3,300, 3,500, something like that. Quite a lot of Tektite papers there. I've looked at most of them, has to be said. Oh, what were we looking for? I diverged. Okay, we're looking at for the seismic line again. I apologise. I've not prepared properly. So what would we go for here for seismic? I produced some diagrams here. Maybe we have a look at final drawings would be a pretty good bet. This was in 2017. Okay, yeah, well this will do. No idea if this is the final version, because I got loads there. Right, let's have a look at the original paper first. My Tektites, how does this work? Got Tonkin papers. This is from Lee et al. 2015. I have a couple of versions. Okay. Right. Let's find this line. 7055 is the line that we were interested in, which is this line here. Okay, very low resolution, unfortunately. Let's move me out the way. Okay, so it's this area here that I'm interested in here. You can see these continuous reflectors here. Continuous reflectors here. This area here, okay, continuous reflector here. This area here is chaotic. It's chaotic. You're starting to get some reflectors back here, but you've got a big chaotic area here. So this area interests me a lot. It's the shallow area that interests me. The top, let's say top 3 seconds of data. So this is time data. So this is continuous here. So let's have a look. This is 1.9 million years old, 5.5 million years old. You've seen you've got a vast amount of sediment thickness. So this age here, this is 1.9 million. Obviously at the surface, that's basically now still sediment being deposited. Halfway down, or a little bit less than halfway down, I mean this line here is probably about 788,000 years is my bet. So above that you've got continuous sequence, below that chaotic sediment. So what I did is I blew this up. Now it's really low resolution, but I blew it up to a similar scale to what was seen in Chesapeake Bay in some of the publications used there. So I blew it up, and let's go to this. Now I'm not a seismic interpreter. I do use seismic in the course of my work, but I'm not actually qualified in doing this, but here goes anyway. So what I'm seeing once I blow this area out, and this is the top 3 seconds of that file there. So I've taken basically this area here, top 3 seconds, right, and then try to have a look at interpretation. Now there appears to be quite a sharp, it looks like a fault here, the edge of something here. Here's the scale, this is 25 kilometers. This is all chaotic beneath this area here. To me there seems to be faults running here, possibly normal faults. There appears to be a crater here. You appear to have some lap out here, which is a good sign, or potential sign for a crater. There's obviously many other explanations, and continuous above. This is likely about 800,000 years, about 788,000 years, this line here. Continuous parallel, chaotic here, chaotic down to basically the Miocene level here. Very interesting here. These are shell diapirs, these areas in green. So this was the interpretation. This is what I published in 2018. So I think we need to get a higher resolution line here. I think it needs to be looked at an expert and a second opinion here. Like I said, let's go back to Google Earth. The next step here, there's one possible seismic line that is for sale. I would like to see it. Crossing here, so I'd be interested in that line. I am very, very interested in this line here, because I think this line potentially is coming close to what would be a central uplift if it is a crater. We don't know if it is, but if it is, it would potentially be crossing or close to crossing the central uplift, so it would be a lot more diagnostic if there is a crater on that seismic line. So I'd love to see that seismic line. In just the top few seconds, even the top 1 or 2 seconds across that area. I think it might be quite diagnostic. So basically this is the summary. I'm sure I've missed out some data, but basically you have a pull-apart basin here, the Yinghai or Songhong Basin. Very, very thick sequence of tertiary sediments, particularly the younger sediments. Perfect tektite source material. and a potential gravity anomaly, potential circular features. Now I don't know how these shell diapirs even factor in. In the published papers, they are generally said to be of an older age. Now, were they pre-existing? Are some of them formed in relation to lines of weakness caused by a crater or an impact? Are they caused by some kind of fracturing or rippling? For me, there's possibly a circular arrangement, and I don't think that can be dismissed. So, I mean, are these, like on the Chicxulub crater, you are seeing around the rim of the crater, you're seeing these cenotes, these sinkholes. Now, okay, this is kind of the opposite scenario, but are these shell diapirs effectively following lines of weakness from an impact crater? Possibly they're totally unrelated, but it's just one line of evidence. The chaotic seismic is more interesting to me in the young sediment, which matches our picture. So you've got a lot of factors pointing there. You've got the distribution, you've got geochemical regression, you've got microtektite regression, which is maybe not as precise. You've got beryllium-10 regression. It's all indicating either this area in Laos or northeast Thailand, which, to be honest, it's on land. I've already explained. There's no big crater lake. You can't erode a crater in that time. I just don't believe it's here. I believe it would have been very much found or flagged as unusual by geologists. It's not a small crater. It's 40 kilometers diameter, most likely. It's not gonna have been missed. There's just no way, and most likely it would have been a big lake, but let's say it's not even a big lake, just for the sake of argument. It won't have been missed by geologists. It's not on land. So, and to be honest, the rock itself is not that suitable. You've got far more suitable sediment on the continental shelf. In fact, incredibly a suitable rock, an incredibly fixed sequence of young suitable rocks. So we are in the Yinghai Basin. It's not going to be really close to land. So you've very much limited yourself to this area. The more west you go, like here, the better it seems. But like I've noted before, we are missing a large amount of data here because it's the South China Sea. You're missing, I try not to get political there, you're missing a large amount of data from this area, so possibly it's skewing things slightly and skewing regression and isoconcentration slightly because you're missing data here and pushing it a little bit more to the west. So I wouldn't rule out something a little bit to the east, but so I'm saying the crater is here where my hand is. Probably here is the optimal place to have a crater, somewhere here. So it's very close to where it probably is, and you've got other lines of evidence pointing there. So I would like to see a lot more research going into this. I believe the data to prove that there is probably a crater, well, it wouldn't prove there's a crater there, but it would be strongly suggesting there is a crater there, probably already exists. It's just not publicly available. It's confidential oil industry data. So hopefully in the future this will be released, even in a very limited form, because it is potentially of huge interest, such a young impact occurring when Homo erectus was living in China up here, and undoubtedly living in here, even though there might not be evidence that Homo erectus was living in Asia then. It's a very interesting event and a huge asteroid collision within the time of humans. Let's get the thing back up. So right, let's get all the localities up. Okay, so these are all the tektite localities again. Huge event. I mean, it's covering a huge part of the Earth's surface. Possible ray distribution, this is speculative. Some of the rays are very well defined, like the Victoria ray, the Victoria ray, the Bickel ray, Manila Bickel ray. There's a very distinctive ray comes through the Philippines there. That's pretty much indisputable, and that goes on out into the Pacific Ocean. We got this Indian rays. There seems to be a bit of a ray going on there that seems quite strong there. So this is roughly the pattern that we're getting, something similar to this. The main downrange ray is likely here, and we're getting samples even in Antarctica, microtektites only. In the downrange range is certainly in this area. So the impactor came in a very shallow angle, maybe something like 15, 17 degrees, something like that. Impacted here, ejected material downrange and along the butterfly rays here. So very interesting, very young impact crater, which is not yet found, but almost certainly is in this area here. It can't be far from this area here. I want to know where it is. So, fingers crossed, somebody in the oil industry with access to such data can get permission to release it, or there is somebody with further geophysical data. Likely this crater is around 40 kilometers in diameter, possibly enlarged to maybe 90 kilometers by slumping, and it's probably buried by about 500 meters, half a kilometer of sediment, possibly up to 700 meters of sediment, but 500 or 600 meters of, or 400 to 600 meters of sediment, probably very realistic. I mean, maybe I work maybe 600 meters of sediment, somewhere like that. It's likely completely buried there. So it's a relatively young event. It should be, it's going to be on the seismic data. At this point, the seismic data will give a good indication that there is a crater there. Drilling it will give the final conclusion. Another thing of possible data is there are a lot of gas wells drilled nearby. If there is wireline data in that younger sediment, say the top 300, 400, 500, 600, 700 meters, there may be a distinct ejector blanket on the logs there, possibly in the cuttings, although I'd be surprised if anyone picked that up. Maybe probably not even picking cuttings at that shallow depth, maybe not even log data at that shallow depth. But if there is any data available, then you could map the ejector blanket and obviously use that data to basically determine where the crater is. So possibly some information exists there. I wouldn't put really any hope on that. The best hope of finding this crater is geophysical data, primarily seismic data. It's going to give a very good indication, and then eventually hopefully this feature will be drilled, and if it's drilled, then you'll get your conclusive data that there is an impact crater or isn't an impact crater there. Now, if there is an impact crater, they can act as good gas reservoirs. I mean, the area is brecciated, so potentially there could be gas reservoirs in this area. So it may be of economic value as well, and that's possibly one reason why the seismic is not readily available. Also, this seismic line is that I'm really interested in. It's a Chinese seismic line. I think it's on the Vietnamese side, so I presume it was shot a long time ago, prior to that maritime border being agreed. So it's of great interest. I'm just trying to switch off the data here. I've got loads of rays. There all the rays are. Let's turn them off. So yeah, possibly very interesting there. So this is an area that needs to be further investigated. There's certainly no proof that the crater is here. There are a lot of strong indicators that the crater is in this area, and then there are possible geophysical signatures and geological features which indicate the crater could be precisely here. A lot more work needs to be done. I hope that in the next 20 years or so that data will be released and that we'll be able to make some scientific advances and establish if there is a crater there. I think it's extremely important and extremely interesting subject, and I really do hope that it comes to some kind of conclusion during my lifetime. Probably got at least another 20 years, but don't leave it too long. You never know. Okay, so happy Asteroid Day. It's 2019. Next year I'll try and get something done on time. I hope I haven't bored you too much. I know people that are obsessed with tektites, and so I'll probably get at least half a dozen views all the way to the end. And but I think it's a very, very interesting subject. I mean, once this crater is found, I can imagine this being big news, and it has huge implications because it is a huge crater, a huge impact, and in human history. And by the way, there is an impact crater. Don't believe some aerial burst or anything like that. Now, let me quickly go into this. Magnon tektites are not formed in situ. They are ejected from the same place as all the other tektites. And tektites are made out of silica-rich rock. The atmosphere isn't. These are ejected, these are blasted over 6,000 kilometres. I mean, if you take all the way to Antarctica even further, but let's just take to Australia, 6,000, 8,000 kilometres is blasted. This is not an aerial blast. Something has hit probably a continental area, continental shelf area, silica-rich sediment, and ejected it. There is definitely contact between the impactor and the sediment. Some of the impactor is found in very trace amounts. So we're talking about 0.5%. If you look at osmium isotopes within the tektite itself. So I mean, there has been a little bit of mixing. There has certainly been contact there. There is a crater. There is a single crater, and it will be found eventually. And most likely, it is in a very thick sequence of young rock, and that limits, in combination with geographic distribution and regression techniques and geochemical regression and so on, it limits it to an area here, further limited to an area here. It's in this area, and if it's not where I say it is, I tell you, it's within 125 kilometres. It's very close to where I'm suggesting it is. It will be found eventually. It's going to be big news, and I think a lot of research will be coming off the back of that, because one of the fascinating things I find about this, by the way, the impact occurred, I'm waffling on now, the impact occurred at the end of towards the end of the glacial period, so sea level was much lower. Likely this area, which is shall I say, was either a deltaic environment or more likely just a very shallow shelf or sea. Perhaps we might be looking at water maybe 30 metres in depth or something like that, maybe less, very shallow shelf or sea, possibly deltaic environment, and ideal conditions really for producing tektites, absolutely perfect. So this occurred towards the end of a glacial period, and maybe there are even humans living right there. Actually, it's a perfect place for humans to live, but it didn't seem to have any significant climatic effects. In fact, it didn't seem to really do anything. Yet you can see the vastness of this event. It was a huge event. I mean, obviously it probably caused a nuclear winter, it caused some cooling, Nothing significant though, doesn't seem to have any significant effect, no extinctions. Everything within about 900 kilometres here would have been vaporised, burnt. There are some papers published by Payne et al. On possible tree falls and such like, possible catastrophic features relating to this impact. But likely within about 900 kilometres everything would have been destroyed and nothing would live basically. But further afield, this is just local. Further afield, pretty much no effect. It would have been probably a bad year or two, but no big effect. But then the order of magnitude of this event is way smaller than the Chicxulub event. I mean, this was probably caused by an asteroid, maybe 2 to 3 kilometres in diameter, maybe let's say 3 kilometres in diameter, something in that order anyway, plus minus. There's some variables depending on impact velocity and type of material, but probably in that order. So yeah, huge event, not as big as Chicxulub, nowhere near, not even in the same category, but yet amazingly, seemingly no real climatic effect. So if we had another impact like this today, I'm sure it would bring the end of civilization pretty much, at least for a period of time, but I seriously doubt it would lead to extinction of humankind or anything. It would be pretty rubbish, but especially if you lived here, because you'll be vaporized. In fact, maybe that's the best place to be. Okay, I'm waffling a bit. Let's do some more research in the Gulf of Tonkin. Let's find this crater. Let's get the seismic. If you can help me out, please do get in touch. I'm readily found on the internet, on Facebook Tektite groups, on my website tektites.info. I'm easily contactable if you want to help out or do a joint thing. When it comes to science, I'm interested in getting answers. I'm not interested in anything else really. I don't make my money here. I'm not an academic, or well, I'm not affiliated with any university. I'm a consultant well site geologist in the oil industry. I'm also a micropaleontologist, although I've not been practicing that for 10 years or so. This is purely out of interest. I want answers the same as everybody else, and I want to understand this event a little bit better. More people involved, the more chance we've got of sorting the problem out. So thank you very much. If you managed to watch the whole of this video, I really appreciate it. Like I said, if I get half a dozen views on this very interesting subject, I'll be happy. So thank you very much, and please do join me for another video if you've not dozed off or you're not in a coma by the end of this. I know my wife would be, she would switch off within about a minute. So she's got no interest in black rocks. She thinks I have far too many. Okay, goodbye and thank you very much.